Let's talk about the gray code next. And so the gray code is set up so that we can progress from one number to the next. Only one bit changes. Each position does not have a definitive weight. This can be quite confusing for counting circuits, but it is ideal for encoders type of circuits. So you want to keep that in mind. What is the purpose that you're trying to accomplish? Gray codes are used with position encoders for accurate control of the motion of robots, machine tools, and several mechanisms. So you can see how in an industrial environment that would be a useful feature for some of the things that you're trying to accomplish. Since only one bit changes at a time, the gray code is considered to be an error minimizing code. For optical encoder disks that use a 4-bit gray code, the encoder disk is attached to a rotating shaft and outputs a digital gray code signal that is used to determine the position of the shaft. Now for ASCII code, this is a way of how we encode numbers, letters in a binary format. And so this is what it would look like here. This is a partial listing of the ASCII code set. ASCII stands for American Standard Code for Information Interchange. There's also an international designation that they use a different name, but it is an alphanumeric code because it includes letters as well as numbers. So this is how you encode it into binary for each one of these things. So even blank, space, that is something that you need to include. The keystrokes on the keyboard of a computer are converted directly into ASCII for processing by the computer. The communication interfaces is done through either an RS-232 or RS-422 protocol. ASCII input modules convert ASCII code input information from an external device to alphanumeric information that the PLC can process. Next, let's talk about parity bit. And some PLC communication systems use a binary bit to check the accuracy of the data transmission. So it's an error correcting feature that you have. When data are transferred between PLCs, one of the binary digits may be accidentally changed from a 1 to a 0. The parity bit is used to detect errors that may occur while word is being moved. Thus, that can be a useful feature because you want to make sure you control things properly. Parity is a system in which each character transmitted contains one additional parity bit. The parity bit may be a 0 or 1 depending on the number of ones and zeros in the character itself. Odd parity means that the total number of bits, binary 1 bits in the character, including the parity bit, is odd. Even parity means that the number of binary 1 bits in the character, including the parity bit, is even. What about binary arithmetic? When adding with binary numbers, there are only 4 conditions that occur. So you can see this, both are 0, it stays 0. If there is 1, then you have a 1 as a result. But if both are 1, then it goes into 0 and you have to carry 1. So this just gives you an example of how that would look like. You can see going from decimal to binary, how that would look. Here just are a couple other examples. I'm going to go ahead and skip this. This is more of a survey that we're doing, so some of these things I won't be able to go into as much detail. So just another example for binary addition. Binary subtraction can be more difficult. To subtract from larger binary numbers, subtract column by column, borrowing from the adjacent column when necessary. When borrowing from the adjacent column, there are now 2 digits, i.e. 0 borrow 1 gives 1 0. So those are things that you can be thinking about. Binary numbers can also be negative. The procedure for this calculation is identical to that of decimal numbers because a smaller value is subtracted from the larger value and a negative sign is placed in front of the result. There are other methods available for doing subtraction. You can use 1 complement and 2's complement. So this sounds a little bit funny, but what ended up being, instead of subtraction, if you take the 1's complement, then you can be doing addition and come up with the correct value. So this could be a simpler implementation, or at least easier to follow. So when there is a carry at the end of the result is positive. When there is no carry, the result is negative, and a minus sign has to be placed in front of it. Sign for subtraction: when there is a carry at the end of the result is positive. When there is no carry, then the result is negative, and a minus sign has to be placed in front of it. Choose complement subtraction: for subtraction using the choose complement, the choose complement is added instead of subtracting the numbers. In this result, if the carry is a 1, then the result is positive. If the carry is 0, the result is negative, and it requires a minus sign. So these are some examples. I'm not going to go through that, so you can pause the video and review that at your leisure. The rules for binary multiplication: when multiplying binary numbers, there are only 4 conditions that can occur. And so here we see those examples. There's only one case when you get a 1 out. So that's when both of them are 1. And so this would be an example of a logic gate AND, which we'll be getting to in a couple of chapters, so you can be thinking about that. Process for dividing one binary number by another is the same for both binary and decimal numbers. So basically, you'd have long division for binary, just like you had long division for decimal. And so I'm not going to go into details, but I'm just giving you an idea of how that would work. PLC data comparison instructions are used to compare the data stored in 2 words. So we can either be sampling to see if they're equal, if one is greater, one is less, and so thus we can have a decision mechanisms. At times, devices may need to be controlled when there are less than, equal to, or greater than other data values or set points. Now, what about floating point arithmetic? This is another thing where we can have another level of complexity that we're starting to introduce. Features of floating point arithmetic: it supports a much wider range of values, and that can represent numbers that are very small or very large. It provides an easy method of dealing with them. So scientific notation would be the way that you can be thinking of what this would actually mean. Here are examples of how that would look. And so you have the base and the thing that you're multiplying by that base, all this laid out here. And we're have everything in base 2 the way it works in a digital computer, and so that's what we're showing. So the left side is a significand or mantissa. I'm more used to the term mantissa, so that's what we're showing here. And the right side of the exponent is the value, and so this is the exponent here that we're showing. The significand or mantissa contains a number, the number's digits, and the exponent contains where the decimal point is located. The decimal floating point numbers usually take the form of scientific notation, with a decimal point always between the first and second digit. Sign, mantissa, and exponent. And so this is how you can be laying it out in a bunch of bits. So the sign is either positive or negative. The mantissa is the part over here that we had talked about, and the exponent is located over here. And so different architectures decide how many bits each one of these are, but the way we're showing it here, we're giving specific values for each one. You can have multiple levels of precision, either single or double. So single would be 32 bits consisting of a sign bit, exponent of 8 bits, and a mantissa of 23. Double precision would have the exponent of 11 versus 8, the way it was before, and a mantissa of 52 when it was 23 before. So that is a comparison. So decimal number 23.5, represented in a single precision 32-bit floating point format, is what we're showing here in this illustration. Okay, well, that's it for this chapter. Thank you very much.